So now that we have some transfer functions under our belt, let's talk about what happens when we go back to the time domain. We're going to start off with first-order systems, which are systems that only have one pole. So the order of a system represents how many independent energy storage variables we have. And for a first-order system, that's one that only has one independent energy storage. So you might think of maybe food in an oven, or putting on, we have a resistor and capacitor. We're going to have a couple examples for mechanical electrical. But if there's only one independent energy storage, then that would be a system that has only one pole and then would be defined as a first order system. So the transfer function would be your residual divided by S minus P if we go back to our MATLAB representation. And since all of our stable systems have negative poles, we're going to see that as some S plus A. So let's say that we have some sort of motor with a torsional damper. We're just going to have an input torque to this motor, and an output is going to be angular velocity. If it was position, we'd bump up to a second order system, so we're going to look at the velocity instead. And we can draw our free body diagram and come up with our equation and find our transfer function of our output velocity over our input torque would be equal to 1 over Js plus B, where J is our mass moment of inertia and B is our frictional constant. Now, we're going to represent that in a slightly different format. We're going to divide by B so that we can have it represented as 1 over B over J over B S plus 1. And the reason for that is that's what puts our system into standard first order format. In standard first order format is a way that we can rewrite our transfer function so that we have only two parameters. A, which is our constant, how much our output is amplified, and tau, which is our time constant, how long it takes for that system to go through. So let's say that we have some input U of S is equal to B over S. Then we can multiply that and say Y of S is equal to A over tau S plus 1 times B over S, which gives us AB over S tau S plus 1. We can use our final value theorem, take the limit as S goes to 0, and find out that we're going to approach AB. If we want to take our initial value theorem, we could say the limit as S goes to infinity would be equal to 0. So we're going to start at 0 and to AB. And if we want to find our full time equation, we could do that through partial fraction expansion. I'll do a full derivation at the end of this video. And we end up with the equation y of t is equal to AB 1 minus e to the negative t over tau. So that tells us that for any first order system, doesn't matter if it's thermal, fluid, mechanical, electrical, if we can get it to our standard first order system format, that means that if we apply a step function to it, we know that eventually it's going to reach AB, and it will take some number of time constants to get to that level, or to approach that level closely. So we take that equation that we just found, and we can calculate that if t is equal to tau, then our output is going to be equal to 0.632 times our steady state value, which is AB. If y is equal to 4 tau, we can say that that will be AB 1 minus e to the negative 4. So it'll take about 4 tau to get to 98% of steady state. So our standard parameters, A, will tell us what our steady state value is. So if A increases, that means our steady state value increases. If tau increases, the time to reach your steady state value increases. So if you have a smaller tau, you have a faster system, and if you have a larger tau, you have a slower system. So let's now have a circuit example. We're going to say that we have a resistor and a capacitor, and we can find our current in terms of our input and output voltage, and get a transfer function. EO over EI is equal to 1 over RCS plus 1. So if we have a circuit like this, what happens is that as the circuit shuts, the capacitor will slowly fill. As the capacitor fills, current slows down, and we end up with zero current when the capacitor is fully filled. When there's zero current, that means there could be no voltage drop across that resistor, which tells us that the voltage in will be equal to the voltage out, so what's stored in the capacitor. And so our A value is 1, which tells us that EO is approaching the value of EI, and our RC determines how long it'll take to happen. So if you have a high resistance or high capacitance, it'll take longer for the capacitor to charge. So I said we'd do the full derivation at the end of the video. So if we have y of s over u of s, that's equal to a over tau s plus 1. U of s is equal to b over s. Y of s is equal to ab over tau s plus 1 s. And now, because we've done all of our Laplace transform in terms of s plus a rather than tau s plus 1, or s plus constant, we're using a already, let's go ahead and divide by tau. So we have ab over tau. And then we have s plus 1 over tau times s. And we're going to want to use partial fraction expansion to get this into the format of r1 over s plus r2 over s plus 1 over tau. And we know that if we combine those, we'd end up with ab over tau. So since there's no s terms, r1 has to be equal to negative r2, and r1 divided by tau is going to be equal to ab over tau. So we find that if we set s equal to 0, which means that r1 will be equal to ab. So y of s will be equal to ab over s minus ab divided by s plus 1 over tau. And so ab over s in the time domain just becomes a constant, ab. Ab over s plus 1 over tau, when we do the Laplace transform of that becomes ab e to the negative t over tau. So that tells us how we got that equation.